new chapter, and that would be chapter 16. Okay. Chapter 16 is about aromatic compound. We already know that there is conjugation, definitions for conjugated system. From chapter 15, we already know what conjugation means. Conjugation means that you do have a double bond separated, two double bonds separated by a single bond. So this is like conjugated diene, versus if you have this situation, this is like isolated diene because it's not separated by only one single bond, is separated by two single bonds here. So aromatic compounds, one condition for aromatic compound is that they must be conjugated. That's the basically secondary. The primary condition for that is that it must be a cyclic system. So it must be cyclic system and it must be conjugated. Okay, that's secondary condition. There is a next condition for that. The 2n plus 2 equals number of pi electron. When you solve for n must be integer. So it can be 0, 1, 2, or 3. Okay, it cannot be a fraction. So 2n plus 2, is it 2n plus 2 or 4n plus 2? 4n plus 2. 4n plus 2 is an equal to number of pi electrons. And when you solve for n, it should be an integer. It could be 0, 1, 2, but it cannot be like 0.5. It cannot be like 1.5 or anything in that nature. So condition 1, it has to be a cyclic system. Condition 2, it has to be conjugated. And condition 3, the 4n plus 2 rule must apply for the molecule to be aromatic. What is unique about aromatic compounds? And that rule, it was the Kekul's rule, and he was the first one who came up with the actually definition for the aromatic, gave the resonance structure for benzene ring, and said that this benzene ring is actually one of the loose structure, is not a whole representation of the molecule. If you want to represent the benzene molecule, you should say that there is also a resonance structure for that. So you show that with the double arrow, or you would draw the cyclohexane ring, and then you would draw a delocalized pi system in there, and normally is shown as cyclohexane with a ring inside. When you look at the structure for benzene, either the resonance representation or a hybrid resonance or combined resonance structures. So the condition, or talking about the conjugated system, your aromatic system must be conjugated, otherwise is not conjugated. If it's conjugated, it means that the pi bond is delocalized. It's not specific to this carbon. If I call this one carbon 1 and 2, is not specific to carbon 1 and 2. It could be between carbon 1 and 2 or carbon 2 and 3, and it goes back and forth. So if you look at the bond length at any given time for any of the CC bond is between carbons, single bond and double bond, is shorter than single bond, but is longer than double bond. That means that it's going back and forth. It's not always single bond, or it's not always double bond. The bond length or the bond order is 1.5. That means you always have the sigma bond, but the pi bond is shared back and forth, half the time is between 1 and 2, the other half is between 2 and 3. So it's going to shift back and forth. And since you only have 2 resonances, then the bond order is going to be 1.5. One stationary, fixed all the time, is sigma bond, and the half is a pi bond that is moving back and forth. Hybridization for every carbon in the benzene ring or in any planar structure that it can be aromatic is a sp2 hybrid carbon. So if you have like sp3 hybrid carbon, it's not aromatic. So if it's all single bonded, one carbon with all single bonded, that means it's not part of the aromatic ring. Characteristic for aromatic compounds. Aromatic means stability. If you remember from chapter 8 from organic 1, if you had a CC double bond, you would test that with Br2. With the Br2 and just carbon tetrachloride, this is going to change to Br and Br. The test is called test for unsaturation. It's very quick test. Br2 is a brown color, but when it's consumed, the color disappears because it reacts with the alkene or saturates the pi bond. You would expect that this to happen when you have a benzene ring, but if you add benzene ring Br2 with CCl4, no reaction would take place. Because if there is a reaction, that means one of these pi bond is going to break. And if pi bond breaks, this reaction is not going to happen. It doesn't form because when the pi bond breaks, this system is not conjugated anymore. And since it's not conjugated and it would lose its aromatic property, as a result, it's not going to happen. Aromatic would prefer to stay aromatic unless you are using harsh condition. And when I'm saying like harsh condition, you're talking about 100 atm pressure or 150 degrees Celsius temperature. So very high temperature, very high pressure, you can destroy the aromatic system. But under normal conditions, you cannot destroy the aromatic system. Destroying aromatic system, meaning that you cannot break the pi bonds, because if you do break the pi bond, the system is not conjugated anymore, is not aromatic anymore, and it becomes unstable and it's not going to go through that. But if you use right and proper catalyst, okay, this is the proper catalyst. If you use proper catalyst, you could do substitution reaction. So no addition reaction, but yes, substitution reaction. And when you say substitution reaction, that means you're removing a hydrogen and you're adding a new group. You're adding electrophile to it. So you have to have very strong electrophile that it can replace the hydrogen. And that type of reaction is called electrophilic substitution reaction. So you bring an electrophile and you replace that with H+. You would have a new product. The reaction is called electrophilic substitution reaction. The resonance energy, the amount of energy that is spent for the resonance to go back and forth, going from resonance 1 to 2, is basically stabilizing the aromatic system. That's why aromaticity means or translate to stability. It is very stable. Heat of hydrogenation, it can be used to determine how stable a compound is. In organic 1, you have learned this, and you should learn in the organic 1. That would be the right place to learn. Heat of hydrogenation is an exothermic reaction because you break pi bond, you add sigma bond, you're adding hydrogen. Like if you add 2 hydrogens here, you are going to change that to cyclohexane. The energy of cyclohexane is lower than cyclohexene, so this energy is going to be released. And how are we sure that energy is released? Because you are breaking pi bond, you are making sigma bond. When you make bond a bond is forming, energy is released. When the bond is broken, energy is being consumed. So if you break a weak bond, you spend less energy. You make a strong bond, more energy is being released. So overall, it's going to be exothermic. So if you get like 240 kilojoule per mole of a diene, that's 2 times as the alkene. That kind of makes sense, right? This is like, it makes sense. You have 2 double bonds, more energy, double of that energy is being released. When it comes to this conjugated, you get almost double, but not exactly double. When it comes to aromatic ring, you would expect to get like 356, 3 times of the 120, but you're only getting 208. That means aromatic system is very stable because the amount of the heat that is being released is showing this molecule has less energy, less internal energy, and lower internal energy, meaning that it's more stable. Any questions? So far, we all agree and we know that the aromatic system is very stable. Okay. In order to add those hydrogens, if you want to saturate it, you have to spend a lot of energy, and it's not going to happen under normal condition. You have to spend high pressure and very high temperature. The molecular orbital theory, it can help us to determine the stability of these molecules as well. So in order to use the molecular orbital, okay, something happened to my pen. For the molecular orbital, there is a rule, and you have to basically draw your cyclic system. This is for molecules that they are cyclic and they do have pi bonds. We want to know why a molecule that is aromatic is stable. If something is not stable, then it means it's not aromatic, based on explanation from the molecular orbital or the pi system. So if molecular orbital, like if the p orbital from one with the p orbital from another, what is happening here? Okay, let me stop this. I have to pause.
So if you have a cyclic system, let's say you have a butadiene. See, the problem is not good, but we can survive this. Okay. Let's say if you have a butadiene and you want to see, based on the molecular orbital, is this molecule stable enough to be aromatic or is not aromatic? You have to draw this structure in a way that is going to only one carbon touches the base energy line. So you basically have to draw this in form of like a diamond shape. And when you draw this, then you have your energy line the energy is going increasing from down up. So this is the energy line. Now you have to follow all these steps. You do have the final picture here, but you have to follow the steps. In every corner, you draw a orbital. Okay, you would draw one orbital. If it's this, first of all, your molecule has to be cyclic. Second, it has to be conjugated in order to follow these rules, and is known as the Polygon Rule. Okay, the Polygon Rule is going to predict if the molecule is aromatic or not. The other rule is that your molecule must follow the 3 conditions for a molecule to be aromatic. Based on the Polygon Rule, you have to first draw the structure of the cyclic system in a way that only one carbon would touch the base energy line. Like if you do this like the way it is here, both carbons are on the same energy level, and that's not going to work for the Polygon Rule, or doesn't apply. The Polygon Rule doesn't apply to this structure, this shape, but it does apply to it. Now you are going to then draw a line that would cut the molecule in half vertically. So if it cuts the molecule in half, and you are going to use like a dashed line, that would cut the molecule in half, and you would call that line a non-bonding line. So you cut the molecule in half, that would be non-bonding. Any orbital lower than energy than the non-bonding is called bonding. So any orbital that you have like this pi is going to be bonding. Okay. Any orbital higher energy than non-bonding is called anti-bonding. Okay. And any orbital that you have on non-bonding is called non-bonding orbital. So for this cyclopentadiene, we have one bonding, one anti-bonding, and 2 are non-bonding. So we have 2 pi orbital that they are non-bonding. Each dashed line or pi bond represents 2 electrons. So we have 2 electrons plus the 2 electrons we have here, 2 electrons. Okay, you have 4 electrons. Now we try to give room to these 4 electrons on these molecular orbitals. These are the molecular orbitals that is coming from the pi bonds, and pi bond forms from the overlap, side-by-side overlap of 2 p orbitals. So since the addition of the orbital is linear addition, basically 1 plus 1 equals 2. If you mix 2 orbitals, that is atomic, you get 2 molecular orbitals. So you would get like 1 bonding and 1 anti-bonding. So if you have like 2 or like 4 electrons, it's coming from 4 different atomic, it's going to give you 4 molecular orbitals. The way this structure shows, we have 2 on the non-bonding line. So we have 2 of them non-bonding, and 1 is bonding, and the other one is anti-bonding. Now, do you remember the Asphalt Principle? How do you give electrons to the orbital? First electron would go to pi 1, pi 2, or pi 3, or 4. First electron. Let me know if you can hear me, so at least when I'm asking, it doesn't come back to me, it doesn't echo. You hear me, right? Okay, first electron would go to which of these pi orbital? 1, 2, or 3, or 4? It would go to pi 1, based on Asphalt Principle. Second electron would go also to pi 1, because it has to first pair up and fill up the pi 1 before it goes to pi 2 or pi 3. This is based on the Asphalt Rule. Orbital with low energy needs to be filled up first. Now, electron number 3 would go to pi 2 or pi 3. Does it matter which one? So it would go either to pi 2 or pi 3, right? So electron number 3 would go to pi 3, let's say. Electron number 4, where should go? Should go to pi 2, pi 3, or pi 4? Electron number 4. Pi 2, and very good. It's going to go to pi 2 because pi 2 and pi 3, they have same amount of energy. So these are degenerated orbitals. Degenerated orbital based on the Hund's rule from general chemistry. Again, they are going to be filled up singly, and then it goes back and pairs up. So we are done with the 4 electrons because we only had 4 electrons. For 2 pi bonds, we only have 4 electrons. So we stop here with the 4 electrons. Now, with these 4 electrons, then we examine, is this molecule stable or not stable? When we look at the molecular orbital, if you have electrons in bonding orbitals and they are paired up, it's very stable. If you have electron in anti-bonding, which is like the pi star here, like this one is anti-bonding, then it's a disaster. That means there is no bonding. It's just trying to destroy the molecule because the bond is not being supported. The electron is an anti-bonding. If you have electron in non-bonding, that means they are there, but they are not forcing the bond to form, or they are not stabilizing the molecule. But worse than that situation, we have 2 single electrons. 2 single electrons, that looks like that you have radical, free radical. And if you have free radical or 2 free radicals, it's just very unstable. So this molecule of the cyclobutadiene is not stable. And if it's not stable, as a result, there's no way that this could be aromatic. It's not aromatic either. Not only is not aromatic, but is actually anti-aromatic. So this is the anti-aromatic compound. So we have anti-aromatic for this molecule. So I'm not going to draw it because it's kind of hard to draw with the mouse, this clean. But this is the benzene ring. I just draw the benzene ring. So you see that for the benzene ring, you have 3 pi bonds. Okay, lead. 3 pi bonds. And if it's 3 pi bonds, it's going to be 6 pi electron. So we have 6 electrons. We draw the molecule in a way that we have 1 carbon touching the base line, and then every corner gets a orbital. Then we draw the non-bonding line. So we have the non-bonding line. The green line shows the non-bonding line. Anything below the green line is bonding. So anything that you have in this region is bonding. So these are bonding. Bonding. Anything that is higher than the green line is anti-bonding. Now, when we're trying to give the 6 electron to these orbitals, the first one goes to pi 1. Okay, this is the pi 1. The second one goes to pi 1 because the same energy has to fill up first. Electron 3 would go to pi 2. Electron 4 would go to pi 3. Electron 5 would go to pi 2. Electron 6 would go to pi 3, and we are done with the 6 electrons. Now, if you look at this structure now, for benzene ring, you have 6 electrons, they're all paired up, and they're all in the bonding orbital. And if you have 3 pairs of electrons, and all 3 of them, all 3 pairs, they are in bonding, that means a stability. You don't want electron in non-bonding. You don't want electron that are in the singly occupied. If you have electrons that are singly occupied, it's going to make the molecule very unstable. Is opposite to stability of our aromatic system, is actually anti-aromatic system. So this is known as the Polygon Rule, that predicts based on the molecular orbital energy, and then finds out if the molecule is aromatic or is not aromatic, based on the other conditions that we had. For molecules to be aromatic, it has to be, the molecule needs to be cyclic, it has to be conjugated, and after it's conjugated, it has to be also 4n+2, it must follow, when you solve it for, it must give you a whole number. It cannot be a fraction. So it's like the Hybridization rule that should apply. So with that information, is cyclooctatetraene aromatic or not? I need your participation. Please help me to decide on this. Condition 1, what's the condition 1? Condition 1 is that it has to be cyclic. So is it cyclic? Yes or no question? We are dealing with the cyclotetraene or octatetraene. Cyclic, right? This molecule is a cyclic system. Yes or no? Can you hear me? Maybe you reply and I don't hear you. Okay. Yes. It is cyclic. Second condition, it must be conjugated. Is it conjugated? Is it conjugated? What does it mean is conjugated? It means it's separate. The pi bonds are separated by single bonds. So you have double bond, single bond, double bond, single bond, double bond, single bond. So it is also conjugated. Condition 3 is that 4n+2 rule must apply. So if 4n+2 should apply, that is 4n+2 equals 8. And can you solve for n? What's the value for n? So this means 4n equals 8 minus 2. If you forgot to do a simple math. So 4n equals 6. And if 4n equals 6, n equals 1.5. And this is not an integer. So if it's not an integer, this is not aromatic. So you could have aromatic, anti-aromatic, or non-aromatic. If the first two condition applies, that means that the system is cyclic and it is conjugated, but the 4n+2 doesn't apply. That means that your molecule is actually anti-aromatic. So this is the anti-aromatic compound. We look at some other examples of aromatic. Let's see. Aromatic or anti-aromatic? Because it's already cyclic and it's conjugated. So it's either aromatic or anti-aromatic. Cyclobutadiene, is this aromatic or anti-aromatic? No response? We just anti, thank you so much. Okay, so this is the anti-aromatic. Why is anti-aromatic? Because we said that if it's cyclic and it's conjugated, but the 4n+2 does not apply. So 4n+2 equals 4. If 4n+2 equals 4, that means 4n equals 2, and n is going to be 0.5, and that makes it anti-aromatic. If n is fraction or decimal, then it's going to be anti-aromatic. Benzene ring. aromatic or anti-aromatic? Benzene is going to be aromatic because the cyclic is conjugated and the 4n plus 2 equals 6. And if 4n plus 2 equals 6, then you can solve for n becomes 1. So cyclic, conjugated, and 4n plus 2 equals 6, n equals 1. So our benzene is going to be aromatic. Aromatic. Cyclooctatetraene, aromatic or anti-aromatic? Thank you so much. It's anti-aromatic. And then decapentaene, this is going to be, if it's planar, it's going to be aromatic. Now, in conclusion, if you have 4 annullines, okay, so if the number of pi electrons is multiple of 4, is going to be the 4 annullines, and is increased by 4. It starts with 4 and then increased by 4 is going to be anti-aromatic. So 4, 8, 12 is going to be anti-aromatic. But if it starts with 6 and you add like 4 to it, so 6, 10, 14, 18, with the condition that it's planar and it's cyclic and it's conjugated, is going to be aromatic. So you have like 4 annullines and 6 annullines. This is known as the 6 annullines, and this is 4 annullines. 8 is the synonym of this 4 annullines because it is increased by 4. Okay. We have talked about that. So just know that the Polygon rule, it involves some steps. I hope that you remember those steps. You have to draw the molecule in a way that one carbon would touch base or energy baseline, and then each corner would take a orbital, molecular orbital, or the pi orbital. You draw the line that would cut the molecule vertically in half. And when you draw it vertically in half, anything below that line is going to be bonding. Anything higher than that is going to be anti-bonding. Anything on the line is going to be non-bonding. So this line is known as the non-bonding line. When you distribute electrons, if electron goes to non-bonding, and if it's going to be unstable. If it's singlet, then it's going to be even more unstable. In a case that is singlet, is classified as anti-aromatic. So we looked at the cyclooctatetraene in 2 ways, and we found that it's anti-aromatic. Cyclobutadiene is anti-aromatic, but benzene is aromatic. So aromatic requirement, as we've been talking, it must be cyclic and conjugated. The atom must be sp2 or sp. That means that it must be planar. That's basically what it says. It must be planar. And the p overlap, p pi orbitals continuously overlapping. This means that it must be conjugated. It's the same thing as being conjugated. And then the 4n plus 2 rule, which must apply. For anti-aromatic, the system is cyclic, is conjugated, but the 4n plus 2 does not apply. That is the problem with the anti-aromatic system. Cyclopentadiene is this aromatic or anti-aromatic or non-aromatic? If you have cyclopentadiene, when you draw the line, the two orbitals are going to be below the non-bonding line. They are bonding, but still a singlet, so it's not aromatic. But if you remove one hydrogen from it and you get like 2 extra electrons to it, the number of electrons from 4 would increase to 6. So it makes the molecule aromatic. So removing hydrogen from cyclopentadiene, it becomes very easy because it goes, your molecule goes from non-aromatic to aromatic. And because it's going from non-aromatic, which is less stable, to aromatic, which is more stable, it's favored, and it's favored because of more stability of the product. Your product is going to be aromatic product. This is a question on the exam. Usually I put this on the question on the quiz and the exam. So just be careful with that. Make sure you pay attention, you understand it. So in this case, your reactant, pentadiene, cyclopentadiene, you do have 2 pi bonds, but it's not conjugated because it's separated by 2 sigma bonds up here. So it's not conjugated because you have a sigma 1 and a sigma 1 here. Okay, the pi bonds are not separated by 1 sigma 1, separated by 2 sigma 1. It's isolated on this end, and so it's not conjugated. It's not continuous overlap. So it's not aromatic. But if you remove a hydrogen, you are removing H plus because you bring a base, and you remove hydrogen. Pair of electron from hydrogen, it will go back, it will be dropped in to the ring, and it will be delocalized. So now instead of the 4 electrons, you have 6 electrons. And with the 6 electrons, the product is going to be aromatic. And in this situation, if you go back to general chemistry, what type of reaction is taking place here is like an acid base. And what is considered a good acid or a strong acid is the acid that can lose hydrogen easily. It is beneficial for this compound to lose hydrogen because if it loses hydrogen, it becomes more stable. That's why the pKa for this molecule is lower, and it compared to other alkane, and it's considered to be more acidic. That means that it can lose hydrogen. But the reason it's losing hydrogen is not that it likes to lose hydrogen for no reason. It likes to lose hydrogen and become aromatic. Okay, just remind me of this slide for next class, and I will cover the rest of the chapter next time. This is just one other example that this OH, when you have a molecule, the dienol, when you have this, if you remove the hydroxide, ion, if it loses hydroxide ion, it becomes positively charged, and you don't have the new pi bonds, the number of electrons, even though it's conjugated, but it's going to be, is not following the Heckel's rule, and 4n plus 2, n would be 0.5, and is not aromatic. So you go from non-aromatic to anti-aromatic. So because it's going from non-aromatic to anti-aromatic, that's why it's not going to happen. So it's not easy for it to act as a base or lose the hydroxide. It's easy for the other compound to lose hydrogen and act as an acid. But you have to basically compare the reactant to product and see in which case you have more stable situation for the reactant or for the product. Slide number 20, the number for